Okay, so you should all be able to hear me and see my iPad screen, which has a very small title of Parton theories. Everything look okay to you, Kabir, over there? Kabir, can you confirm?
Yes, we can hear you. We can see the screen as well, yeah.
All right, great. So sorry for the delay. So let's get started then. So what I'm going to begin this lecture with is just a kind of a bird's eye view of various topological and exotic phases of matter that have been studied in condensed matter. And I'm going to give a view using the Parton approach. This is an approach we have already used quite extensively in the theory of the Zito spin liquid. And generalizations of it are extremely powerful and allow us to really understand essentially the complete library of interesting phases that have any connections to experiments using very similar methods. So I'm just going to make a table or survey of the different phases you get from the Parton approach. Certainly I'm not going to cover most of them in the class because there's just not enough time. I have covered most of these topics in other times I've taught the course, and there will be, when my book eventually comes out, there will be chapters on really most of the things I'm going to mention today. But I just want to give a rough overview, and hopefully you'll get the main idea. All right, so what I'm going to show is a bunch of tables, and the tables have two columns. So on the left column, we consider, either bosons or fermions or some mixture thereof with some weak interactions. And then ask, what are the familiar trivial phases bosons can form. So with bosons, we know that, the most obvious thing they do in weak interactions or even free bosons, they both condense and you get a superfluid. Now, we were interested in strongly interacting systems, like a system of spins. And the method we've used is we use the Parton approach. We split the spin into two bosons. These bosons carry spin a half, unlike the spin operator, which is transformed under spin 1 representation of SU2. So now you can ask, once you do this, and these bosons are nearly free, these partons are nearly free, what kind of phases do you get on the right column? And the difference is in the right column, of course, once you make a Parton decomposition, there's a gauge field. There's some kind of gauge symmetry introduced anytime you make a Parton decomposition. And so you have to worry about the effects of the gauge field. And that's what we spent several weeks now on what the effect of the gauge field was and got a theory of the Z2 spin liquid in a particular theory of these partons. So the idea is that on the left-hand side, you have some simple phases of bosons, the fermions, and on the right-hand column, you have the more complicated phases of matter you get once you remember that there's a gauge field. Okay. All right, so if bosons form a superfluid, now suppose it's the partons that form a superfluid, what phase of the spin system does that correspond to? Well, it's easy to see. This is not something I spent too much time on, but let me just comment on it. It's easy to see what you get is just the magnetically ordered state, some kind of nail state or ferromagnet, something like that. And that state that we get is not an exotic state. It's the same state you'd have gotten if you hadn't worried about the gauge symmetry. And why is that? Well, the reason is when the boson condenses, it essentially breaks the gauge symmetry completely. So, there's a gauge symmetry of B going to B, as an index here, e to the I phi. And what do I mean by statement that the gauge symmetry is broken completely? Well, if I have a condensate where the bosons condense, then there's no gauge transform I can make which leaves the condensate invariant. So, if I take any gauge transformation at all, it changes the condensate. And when that's the case, as we've seen in some of our computations, the gauge boson, the massless gauge boson that you may have had because of the gauge symmetry, becomes heavy, acquires a mass, is not so important. So that's we say that the gauge symmetry is completely gauged in this case, and so we don't have to worry about it. On the other hand, once you condense B alpha, you necessarily break spin rotation symmetry because there's no choice of B alpha that leaves all the spins invariant. Remember, of course, this B alpha has a constraint that B dagger B equals 1. So if you choose any condensate which leaves this invariant, you'll find that you'll always have some non-zero expectation value for S. So for those two reasons, there's always a non-zero expectation value of S, and the gauge symmetry is completely gone. That tells us that this phase is in some sense a familiar phase. It's a phase with a broken symmetry and nothing more. Okay. All right, so so then let's go to what we actually did. But what we did, if you remember, was condense the Qij. And the Qij, the Qij were Bi, a product of two Bs with some epsilon symbols I won't worry about. So this is a condensate of pairs of bosons. Okay, so it could happen if you have ordinary bosons that for some reason there's an attractive interaction between them and they form a molecule, and it's the molecule that condenses it. And that's effectively what we did in our theory of the Z2 spin liquid. So why is that a Z2 spin liquid, at least on the triangle lattice? Well, because this condensate, now there is a gauge transformation which is left over. And that's the gauge transformation B goes to minus B. That doesn't change the condensate. And it's that Z2 gauge transformation that led to all the physics that we were discussing the last 2 weeks. So paired superfluid of bosons is just a Z2 spin liquid once you put the gauge symmetry in. Okay, now you may remember we also looked at the case of the square lattice where we had this paired condensate. But because of the sublattice structure, we found that actually there's a U1 gauge symmetry that's still left over. And we didn't treat that. And I may say something about this in the next lecture. So that leads to some field theories of the CP1 model, which is dual to another model. And I may say a few things about this very briefly. But really going into this detail would be really the rest of the course. Okay, what else can you do with bosons? Well, unfortunately, it turns out not very much. Bosons are kind of hard to deal with. Now, in the recent times, people have discovered that strongly interacting bosons can have what are called SPT phases. I'm not going to go into that. And if these bosons have a SPT phase, and then you gauge the bosons, make these B alpha bosons be in the SPT phase, then you'll get the chiral spin liquid, which is the phase we're going to discuss today. But this is a complicated construction and seems not worth the trouble. Why introduce partons if the theory is complicated in terms of partons too? You want to choose partons in a way that you simplify the theory, not make it more complicated. So I won't really say anything about that. Okay, however, with fermions, we find that hold the floodgates.
A naive question before we go further.
Yes, please.
I have heard this comment that gauge symmetry cannot be broken in the sense that it is just a redundancy in the description. But here you are saying that gauge symmetry is completely broken in some of the phases. Can you clarify this point?
Yeah, okay. So I think it's a bit of a semantic point, and perhaps I shouldn't have used broken, but it's a word that's commonly used. Of course, any physical observable has to be gauge invariant. But when I say a gauge symmetry is broken, what I really mean is that if I fix the condensate, and if I choose the condensate to be constant, then the gauge transformations that change the condensate are no longer relevant. And therefore, you will find that various objects you thought But photons are not really gapless. I mean, maybe that's another way to say it, but that's kind of mouthful. So we just say it's broken. But of course, there's something called the Lipschitz theorem, which says that no gauge, I mean, that's kind of an empty statement, really, just a statement that something that has gauge transformations is something that has a gauge charge cannot acquire an expectation of it. Another way to say it is that the state of states, the space of states we're looking at, in our Hilbert space are all gauge invariant states. They have zero gauge charge. And I'm always doing that. And the statement that something is broken is simply a statement about a choice for the gauge choice for the object that's condensed. Okay. Yeah, we could go on about this, but I think that's my best understanding of it. Somehow I wish, everybody knows Ellipsis paper, but it's very, very misleading. I would suggest, read Weinberg's book. He breaks gauge symmetry every second page. And okay, if you're not bothered by that, you shouldn't be bothered about what I'm doing. Yeah, maybe you can say it better, Tom.
Well, this was all understood very well in the 1970s.
I'm sure.
You can do a transformation, change of variable,
Yeah.
in which the description, the semi-classical description that you call spontaneously broken gauge symmetry is completely formulated entirely in terms of gauge invariant operator.
Yes.
And the only issue with that in the continuum is that that theory doesn't look renormalizable. And you have to go to other gauges to see that it's really renormalizable. But there's absolutely no issue with Ellipsis theorem.
Right. So
What we call spontaneous gauge symmetry breaking is an entirely gauge invariant precision.
right. Okay. So and the other comment I'll make, but I get this question a lot. So maybe just to avoid the confusion, rather than using the terminology gauge symmetry has been broken, we just say the gauge symmetry has been Higgsed. And that maybe is a little less confusing. So I'll try to do that. Of course, yeah, all right. All right, so now I said, well, let's do this with fermions. Okay, so, we've studied weakly interacting fermions or electrons, and the simplest thing they can do is form a metal or a superconductor. And what would happen if I now express the spin in terms of fermionic partons? This is something you can also do, and I'm going to do that today. What would happen if you took this state of gauge invariant fermions and just took it as a starting point for partons? So I take fermionic partons which have a gauge charge, but I just assume they're forming this state on the left column. All right, so in this case, we take partons. They'll also form a spin-on Fermi surface, and rather just like electrons form a Fermi surface. And now we'll call the partons spin-ons here. And the partons on the Fermi surface will interact with the gauge field. So this is not quite a free Fermi problem. It's not a Fermi liquid. It's a very complicated state of matter, which under certain conditions now is pretty reliably been shown to be stable. The experimental evidence of it is, not convincing yet, but it's possible someday this kind of spin-on Fermi surface will be seen in experiments. And I'll probably say something about this towards the end of the course. So we can call it a spin-on Fermi surface or a Bose metal. This is another word that's used for it. Okay, then the other simple state that electrons can form is a BCS, a paired state, a BCS superconductor. Here I'm thinking of electrons as, not worrying about the charge of the electron. I'll have some comments on that in a minute. So maybe a better word is these are helium-3 atoms, and they form a BCS superfluid. Okay. So the charge is really a global symmetry of conservation of helium-3. Now, so you've got, so now what's going to happen? So now you have an FF condensate. And the FF condensate Higgs is the U1 gauge symmetry down to Z2 in exactly the same way that BV condensate takes the U1 down to Z2 over here. Okay, and in fact, this was the calculation that was done by Wen. I haven't discussed it, I won't go through it. And what we understand today is that the Z2 spin liquid you get from this approach is essentially the same as the Z2 spin liquid you get from this approach. So these two Parton approaches give you the same theory. In the sense that in this theory, we learned that the Z2 spin liquid had a spin-on, which was a boson, which we call the E particle, and a Wison, which is the M particle. And the bound state of the two was a fermion, which we call the epsilon. And what happens here is the converse. The spin-on is the F particle, so that's the epsilon. The Wison is just the same, it's always a boson. And now the bound state of this F and the M particle is the E, which is this B. So now you see that this B here in the Z2 spin liquid is a bound state of this F and the Wison. So that's all been shown in very nice detail and very beautiful papers. I think Ashwin Vishwanath especially wrote several of them. All right, so we've got one new state, which I won't discuss now, but now fermions, unlike bosons, can do something else very interesting. They can have non-trivial band structures. And this goes into the field of band topology. So the earliest one was discovered by Thales, or TKKN, part of it mentioned in the Nobel Prize citation, that they can be insulators, electrons, moving in some periodic potential. He had a non-zero magnetic field, and then Haldane showed you could even get a net zero magnetic field, which now would be called a Chern insulator. So what does this mean? That there's some band structure, which is characterized by a topological invariant. This means that as you change the potential or slowly of some crystal, as long as you don't close a gap, you'll never change the Chern invariant. And so this band structure will be totally disconnected from any other band structure. So each band structure is characterized by a non-zero Chern number, and that forms a topological class of band structures. And once you have a non-zero Chern number, then you get also interesting stuff like edge states and so on. So that was the starting point of what are now called topological insulators. That name is a bit unfortunate because also for quite a while, when people talked about topological insulators, they meant insulators with anyons, like on the right column, like a Z2 spin liquid. So now I've been very careful to not call it a topological material. Previously topological meant non-trivial degeneracy on a torus. Now it doesn't, at least to experimentalists, which means it's hopeless to go back to the old terminology. But it's a point of endless confusion for students especially. Anyway, so topological insulators, the simplest example of a topological insulator is a Chern insulator, which has a Chern number. And in fact, that's what I'll talk about today. So when you take a Chern insulator, when you take these fermions, the spin-ons now, and you put them in a Chern insulator, then you get something non-trivial. Then you get a theory with anyons, because there's a gauge field here. And that's the chiral spin liquid. So that's what I hope to talk about today, but let's see how much time I have to talk about this. So today, the plan is to do this Parton construction, obtain a Chern insulator, and then show that when you gauge it, you get a chiral spin liquid. Okay, so now you can continue this. And now, surprisingly, the full classification of band topology didn't happen until about 10, 15 years ago. Particularly many different. So the thing about the Chern number is that it's non-zero only in a system that breaks time reversal symmetry. You require a magnetic field or something, or some kind of something that breaking time reversal. And what Kane and Mallet found rather late in the game, but quite amazingly, experimentally very relevant, is that you can get insulators which are characterized by a Z2 topological invariant, not an integer, just a sign, which preserves time reversal symmetry. And many examples of these now known in experiments. And again, this Kane-Miller insulator with a Z2 topological invariant has really nothing to do with the Z2 spin liquid that we talked about earlier. Yeah, so there is a very confusing terminology, which I'm trying to at least explain as clearly as I can. So in fact, there's something called the tenfold way, which is a complete classification of band topology, not just of electrons, but also of electrons which are paired. So we imagine that's a relatively simple thing you can do, just pair the electrons. But then there's a further confusion there, depending on whether you consider the charge of the electron to be a global symmetry or a gauge symmetry. If you consider a global symmetry, then yes, then these phases you get by putting electrons in a topological band structure in a superconductor. Topological superconductor it doesn't have any anion. So that is the true, for example, helium-3. Helium-3 is a topological superconductor in the sense of the left column. Doesn't have any anions, but it does have a non-trivial band topology. However, with electrons, it gets a bit confusing. Once you allow for magnetic fields, then the global charge symmetry is really a gauge symmetry. So these topological superconductors do have something like a gauge symmetry, and they do have anionic objects, but they're not that easy to access. And anyway, but that's also the focus of a lot of experimental work. Okay, so that's another somewhat confusing connection between this left column and the right column. The easiest way to think about it, I think, is just consider electromagnetic charge symmetry of the electrons to be just a global symmetry. Then these are topological superconductors in the sense of band topology. So in particular, if I take a P plus IP topological superconductor of the spin-ons, so take some spin-on theory, pair the spin-ons, and then choose a band for the Bogoliubov quasiparticles to have a certain topological invariant. Then you get a highly non-trivial state, which has many different names. It's the Ising topological order. It's also the non-trivial phase found in exact solution by Kitaev. It's the phase people have claimed may be found in ruthenium chloride, but although I think the evidence for that is slowly dissipating. And what's exciting about it, of course, this is a phase with non-abelian anions. Okay. I won't talk about this in this course, but there are some notes that will eventually appear in my book on this. All right, so that's how the most simplest general way of understanding what this Ising anion phase is. It's simply a phase where you take these spin-ons and put them in a P plus IP superconductor. Okay, now fermions can do other things. They can form a gapless Dirac spectrum, like in graphene. You can have fermions forming a Dirac node, or they can form wild nodes in 3 dimensions. So then you can ask, well, would that happen to spin-ons? So then you take a Dirac spectrum, and you take spin-ons with the Dirac spectrum, and then couple them to a gauge field. So there's literally an infinite number of papers written on that. It's still an evolving situation. On the triangle lattice, it seems you could get a low energy theory, which turns out to be quantum electrodynamics. There's a U1 gauge field coupled to 4 massless Dirac fermions. It's still an open question in the sense of field theory, whether this field theory, this is a conformal field theory, whether it exists or not. Anyway, it could exist, but people are still debating it. And if you do it in the square lattice, you get this theory, you get an SU2 gauge theory, not U1, and that's something we can talk about, with two flavors of colored from Dirac, massless Dirac fermion. And this is also can be rewritten as this SU5 level 1, SO5 level 1 depressing a Witten model. And there's again a very interesting post-Fermi duality because this theory here obtained with fermionic partons turns out to be the same as this theory here obtained with bosonic partons. So that's something that Wang et al. Talked a lot about recently. Also something we will talk about a bit. You could take electrons and put them, give random interactions between them, as in the Kitaev, as Kitaev did for his Majorana fermions. And if you did this for complex fermions, you get the complex, what's now called the complex SYK model. It's some kind of non-Fermi liquid model of electrons. But if you did it with partons, you can get a very similar state. And that was actually the state that I looked at with Y many years ago. So let me just call that the SY spin liquid. So there's a subtle distinction between the SYK state and the SY state. One has a gate charge, the other one doesn't. That certainly makes, it doesn't make very much difference in the large N limit, but it makes a big difference to what are observable operators in the system. Okay, any questions on this table?
Yeah.
Yes.
So all of these descriptions, if I think in terms of the Hubbard model,
Yeah,
this is the strongly coupled model at half filling.
the right column.
Yeah.
Yes.
And-
Some spin model on some lattice.
Right.
Yeah.
So now, do they naturally extend away from half filling? Okay.
Not in an easy way. So
No.
that's, of course, what I want to talk about in the rest of the course. That's still a problem of current research and of great, much more experimental importance as far as the qubits are concerned. There's literally no shortage of experiments or things like that. Whereas these are, very exotic things that on this right column here, which few materials have been found here and there, which you can maybe see some of these phenomena. Okay, any other questions on this table? So I spent some time thinking about this table, and I think it's nice the way it unifies many different things.
I have a general question about Parton construction.
Yes.
How does one define the gauge group? Is it the set of transformations which leave the physical operators invariant, or is it the set of operations which leaves the non-physical part of the Hilbert space invariant, or are these definitions the same? I'm a bit confused about that.
Yeah, that's a great question. So let me just start. I think the way to do it is you have some Parton decomposition. So certainly the maximum possible gauge group you could have is one that leads this gauge invariant operator invariant, say like the S. So you introduce these boson partons, and now you want to see what's the maximum possible gauge group that you should worry about. So in this case, for this case, it's U1, that B goes to B at E to the F5. That's the biggest transformation that leaves this decomposition invariant. Okay, so that's step one. Then step two is you now take these partons and write down some theory, and that theory will have some Higgs fields. Depending on what kind of interactions you have, you'll introduce a bunch of Higgs fields. And then you have to ask which of them are condensed. So that's a dynamical question, and not something I can tell you ahead of time. You can sit down and make a guess, and then you figure out how well that fits with certain numerical study or something like that. But that's really the hard part, deciding what are good Higgs fields and which of them are going to condense. But once a few Higgs fields condense, then you have to decide what's the largest gauge group, which will be a subgroup of the gauge you found here, which leaves the Higgs field invariant. And then that will tell you what the remaining gauge group is around, under which your anyons could have charges. So that's I think, a fairly foolproof, but very difficult to implement task. Now, so one subtlety here, which I think I will say a little bit about, maybe not, probably not today, definitely not today, is that this decomposition, if you look at it, it seems like it has only the same, exactly the same largest possible gauge group, which is F going to e to the I pi times F. That leaves it invariant. That's certainly true, it leaves it invariant, but it's not the largest possible. There's actually a bigger transformation. It's an SU2 transformation, not U1, which leaves this decomposition invariant. And I've already put up notes on how that works on the website, and I think I will say something about it next time. So that's why under this Parton construction, sometimes you can end up with SU2 gauge fields. All right, so let's getting towards strong questions. There are other sets of problems which I won't talk about this course, but I just want to mention for which the Parton construction is also extremely powerful, although traditionally it's not the way the theory has been worked out in the literature. But you can do it, and doing it this way has actually many advantages. And these are the fractional quantum Hall states. So if you just have non-interacting electrons, well, the only thing they can form when in a magnetic field is an integer quantum Hall state. That's the IQH. Okay, so how do we get fractional quantum Hall states? Well, to get essentially almost all the observed fractional quantum Hall states, what you do is you take your electron now. Previously, we were fractionalizing spin operators here and here. So now we're going to fractionalize the electron operator itself. I'm ignoring spin because that's an additional complication that could be important in some cases.
So C is the electron then?
C is the electron. So you write the electron in terms of 3 partons, F1, F2, F3, which are all fermions. Okay. And now you can ask, let's treat these partons as nearly free and put them in some state in a magnetic field and then put back the gauge fields and ask what you get. Okay, so when you do this and you put all 3 of them in fully filled Landau levels, or equivalently in Chern insulator bands, fully filled, F1, F2, and F3, all integer quantum Hall states or Chern insulators, then you will get the full sequence of Laughlin and the Jane fractional quantum Hall states. This has been known for a long time. I think Jane pointed this out many years ago. What's perhaps a little not as well known is that you can use this Parton construction in addition with all these tricks with gauge theories to get really a very well-defined and completely controlled calculation of the low-energy field theory of the quasi-particles in their statistics and also topological degeneracy on torus. Now, traditionally, the way this has been done in the condensed matter literature is using something called a flux attachment transformation, which I know people in this room find unpalatable because it leads to funny things like Chern-Simons terms that are not properly normalized. Now, I'm not saying the results in the condensed matter literature are wrong. I mean, to the problem they were addressing, they give correct answers. But if you're a purist and really want to understand the topological properties, even on a torus correctly, you can't use those approaches. But this one works perfectly fine. It gives you everything correct, as far as I know. All right, so that's one possible result of this, the Laughlin and Jane fractional quantum Hall effect. This actually gives you the 1/3 state. The simplest example is both F1, F2, F3 occupy a single Landau level. That's the Laughlin 1/3 state. And the Jane states, the whole sequence around 1/2, you can get also by this construction. The 1/5 state would require 5 partons, but let's not go there.
So Laughlin state is you occupy the 3 fermions, F1, F2, F3, or only just, let's say, F1?
I can hear say that again.
So to get the Laughlin state,
Yeah.
Do you occupy the 3 fermions, F1, F2, F3, or only one of them?
All of them. So there's a simple picture you can draw. So you have 1/3 filling. You have 3 flux pointer coming in for each electron. Okay. So here are 3 flux pointer. Now each electron splits into 3 fermions, F1, F2, F3. And you imagine these flux quanta act on F1, F2, and F3. So each one of them, F2 and F1 and F2, F3, have one flux quantum per fermion, and they'll form a nu equals 1 integer quantum Hall state.
Oh, I see. Because the fermion has charge 1/3, the F has charge 1/3, so the flux quantum is less.
Yes,
Okay.
yes. And if you to get the Jn fractions, you have to do something like maybe a 4 plus quanta, and the 2 of them will go here, one will go there. That will give you some of the error. Yeah, yeah.
Do you have to introduce Z3 gauge fields or something?
Yeah. So, well, the most general thing you probably have to introduce an SU3 gauge field, because this whole thing is invariant under SU3 gauge transformation. But we imagine that there are certain, certain Higgs fields that will break it down. I think the theory that seems to give all the right properties is U1 cross U1. There's a U1 here and a U1 here, and once you introduce them, you get everything right. In fact, you wrote these papers with Senthil and Wang on fermion boson dualities. You can derive all of them also by this kind of Parton construction, very simply with 2 U1 gauge fields. All right, so there are now some other states you can get by this approach. You could imagine that one of the partons is effectively in 0 magnetic field, this one, so that will form a Fermi surface, and the other partons form, so there's a magnetic field, form a integer quantum Hall state. So in this case, they're a filling fraction 1/2. So you have 2 flux quanta, 3 partons, and they go into 2 of them, F1 and F2, and there's no magnetic field on the 3rd one, so that will form a Fermi surface. And then if you do fluctuations about this and integrate out these filled bands, you will get the HLR theory for the half-filled Landau level. That's the Halpern-Lee theory. But that's integrating out the fully filled Landau levels is a subtle thing, especially if you have boundaries or you're a torus. But if you're considering the infinite volume plane, you get the HLR theory correctly. But on a torus or with boundaries, you will get the correct theory, which sometimes the HLR theory doesn't get quite right. Okay, so another thing you could do is exactly at nu equals 1/2. What happened there? Oh, I lost everything. Okay, so if you have nu equals 1/2, then you have, oops. Excuse me. Yeah, you have 2 flux quanta, and then you have 3 partons.
There's a question about what are the commutation relations between F1, F2, F3? Do they?
They're fermions, which have the usual Fermi computation relation. You can think of 1, 2, 3 as some kind of spin label or color label.
But for a single electron, there is a 1, 2, 3 associated with it, and for another electron, there are another 1, 2, 3, and there is no special relationship between the Fs for one electron and another electron.
Yeah. I mean, these are. It's really very the same as here, except I'm using the C operator rather than the spin-on operator. So here there's if you want to put everything on a lattice, that will make it even clearer. Put everything on a lattice, and there's an I label that I've dropped here. It's the same I on every site in the spin and the Fs. And you can do the same thing here. There's a Ci, F1 of I, F2 of I, and F3 of I. So you introduce 3 fermions that can sit on that site. Now in Hilbert space, there's a constraint here. There's a big constraint that the number of C is equal to the number of F is equal to the number of F1 is equal to the number of F2 is equal to the number of F3. So now you have several constraints and therefore more gauge fields to worry about. So a bit more complicated, but very much in the spirit of the type of calculation that I'm going to present. Sure. I'm not going to go through any of this, just telling you this can be done. And this is probably the simplest way to unify many papers in the condensed matter literature. Yeah, I mean, I didn't work on this stuff. I found the literature very, very confusing, and when I found that I could understand it in the Parton approach, I felt much better. Everything is really
Thank you.
nice. Okay, so what I was saying is that in this final case, at nu equals 1/2, you have two flux quanta, and maybe they go on the two Parton, they form integer fill Landau levels. And the last Parton has no magnetic field, so it forms a Fermi surface. And then these fermions can pair to form a Cooper pair, and they have to do it in a px plus IPY form. And when they do that, you will get the Moe-Reed non-abelian fractal quantum Hall state. And you can get, again, the full theory of it by carefully worrying about all the gate symmetries in the Parton decomposition.
It has to be px plus IPY because they're spinless.
Yes, but also you need edge states on the. You need a non-trivial. This px plus IPY has topology in the sense of band topology. So even free fermions in that the Bogoliubov quasi-particles have Majorana edge states. So you need those. So that it's again there's some topology that comes from the band structure. There's the other topology coming from the gauge field, and you have to put it all together. Yeah.
Which of all these fields have spin a half of spin zero? So you have bosons and fermions, and some of them have an index alpha, which is like
So when here I'm talking about spin systems, then they do have a spin. Here, the simplest case is just ignore spin. There's a Zeeman field, have all electrons are spin off. Let's just imagine. That's the case I'm considering. You can certainly generalize it to a case where you have spin, and even some spin down electrons are involved, and then but it's just an extension of what happens.
So should I be thinking about C and all the Fs and all that as having spin zero?
Yes, yeah. They just spin meaning they're all spin off. That's it. There's a huge magnetic field, and they're all spin off. That's the simplest case. Of course, you can put it back in if you want, but it's the same approach. All right. And finally, to answer Tom's question, this is something I will say much more about. This is probably the proton approach that we use the most in the literature for doped spin liquids, like the cuprates, where you get high temperature superconductivity. So there you take the electron and you decompose it into a product of a fermion and a boson. Now, I purposely haven't put a spin index because depending on who's writing the paper, the spin index could go either on the fermion or on the boson. And these constructions will give you somewhat different states. All right, so I'm going to address this in much greater detail. I guess the main comment I would make is that, roughly speaking, this Parton construction doesn't really work. It's nowhere near as successful as all the others that we discussed. And one of the reasons it doesn't work is that what's causing the fractionalization is the exchange coupling, which is about a J. But what wants to bind them together again is the hopping. The thing that hops the objects is the electron, is the hopping T, which is much bigger than J. So this particular fractionalization approach has some of the right physics, but it just doesn't give you a good correspondence to experimental data. Anyway, so this is in some ways still an open problem on how to fix this, and we have some ideas that maybe I'll mention towards the end of the course.
I have a question about that.
Yes.
So it's actually about all of these tables.
Yeah.
What do we actually learn from that? Do we learn that we start from one system, we rewrite the variables differently, and change the parameters, and somewhere in the space of couplings, we can find this phase?
Yes.
Or is there a stronger statement than that?
No, that's all. So what I was just saying was that all of these phases you find on the right, at least the last two, where they are well behaved, is where the exchange coupling is much larger than the hopping. Whereas in the real world, the situation is the opposite. The hopping is larger than the exchange coupling. And it's still an open problem on how do we understand possible exotic non-Fermi liquid phases in the regime where the hopping is bigger than the exchange. We have some recent papers. We think we've made a lot of progress on it, but referees gave us a lot of trouble with those papers, but I think we're onto something. Okay, but that's part of the course in this field anyway. But one thing I should mention, so there is something called the slave boson, or now better called the hybridization boson, that appears in a somewhat different context as the Kondo lattice. So in the Kondo lattice, you have two bands. There's one band which is spins, which are effectively like any of the spins that we're talking, any of these states we're talking about here. So that's one band. And there's another band, we have moving electrons. So, and for that coupled system, there is a very beautiful theory, originally due to Coleman and others. And that's been very, very successful by introducing another one of these partons, this slave boson or the hybridization boson. But what I want to say is it's not really a parton. What the best way to think about it is that the spins have a spin on. So there's fractionalization of the spins, but the conduction electrons don't fractionalize. And this hybridization boson is really a bound state. It's not the splitting of anything, it's the bound state of a spin on of the spin band or the F electron band and the electron in the conduction band. Okay, and again, this is something I probably will say something about in this latter part of the course. All right, so that took much longer than I thought, but hopefully it's useful for you to give you a bird's eye view of the very rich variety of phases that people have been studying and their relationships. The broad division is that the two main effects are, one is that, of band topology, just having a certain band structure can give you a lot of interesting topological effects, including edge states. And the other effect is due to gauge fields. And the interplay between these two is amazingly rich. You get a huge rich variety of phases, well beyond the simple Z2 spin liquid we talked about. Okay. All right, so now I'm going to use the board. Disconnected. Okay, so if you can see the board and also hear me. All right, so I'm going to talk about the chiral spin liquid. So here, the basic starting point is on each side I introduce fermions rather than bosons, along with the constraint that F dagger I alpha, Fi alpha on every site is equal to 1. So the Hilbert space of state on each side is as the up state, which we think of as a fermion acting on the fermion vacuum, and the down state, which is the fermion. Okay, so this is exactly what we did for the Z2 spin liquid, except using fermions rather than bosons. And why are we using fermions? Well, the reason is fermions can have a non-trivial band topology. Bosons, well, they could have non-trivial band topology, but what they will do is go to the lowest energy state and condense in it. So you won't really be sensitive to the band topology in the ground state. So that's why bosons are not very good. Fermions, however, will feel the bands even in the ground state. Okay, so right, so I'm going to take some Hamiltonian, some set of Jij on the square lattice. And look at a certain mean field theory, very similar to the mean field theory we did for the bosons. And this kind of thing was done, I think, early on by Wen, Wilczek, and Z. They did it of a particular model in square lattice. Now today, there's no evidence that that particular model has a chiral spin liquid state. This is a mean field approach. It's not very powerful. But what people have done, what's developed in the intervening 20 years is a lot of very powerful numerical methods. And now there's quite a catalog of specific models in this category. Some of them break the SU2 global symmetry, which is not crucial for anything I want to talk about. So there's quite a catalog of such models that do in fact have a chiral spin liquid ground state. There's very good numerical evidence for that. So I'm just going to work on the square lattice, but I imagine one could work on whatever lattice you wanted and come up with a similar theory. So this theory, what I'm doing now can't predict whether the approach is going to be successful or not. You really have to do the hard work, which has been done by many people. Okay, so you take this interaction here. So you take S1 dot S2, and after some identities and using this constraint, just like we did for the bosons, you can rewrite it in a way that motivate the mean field theory we're going to look at. Well, there's various ways to do this. There's one way to write it in terms of F dagger terms, another way to write it in terms of F dagger F terms, but this is the way useful here. This is -1/2 F dagger 1 alpha, F2 alpha, minus F dagger 2 beta, 1 plus some constant. So previously, you may remember for fermions, for bosons, I had a B dagger with an epsilon tensor. You can also do that with fermions. There's two different ways of writing it. We're going to just choose this. And why do we choose this? Well, ultimately, there's no justification right now. It's only, well, we get a certain state when we're done with this analysis, and then we have to do a full numerical analysis to see if we got the right state. Okay. None of them give the right answer in this case anyway, so, right. All right, so now you've got this interaction. And so I'm going to decouple it by the usual tricks. So this thing I'm going to write by Hubbard-Stratonovich transformation as J12 over 2 as Q12 mod squared minus, okay, there's a typo there. Well, okay. Qij F dagger I alpha, Fj alpha plus summation quantity. Okay, so if I integrate over, sorry, let me make it very general, Jij, there probably is a Jij over here too. Yeah, so Hamiltonian sum on Ij of this. So again, the parallel of what we did for bosons, except there's some Qij that decouple. And so now really it becomes a choice, just to look at some saddle point. And it's a saddle point where you're going to now look for optimal values of the Qij. So that's a task that people have gone through. And so we're just interested in general feature rather than actual numbers. So we want to look at, what are the type of interesting saddle points you can get that gives us interesting spin liquids once we put the gauge field back in. Okay, what about the gauge field here? Here the gauge transformations are very simple. And you might wonder why I didn't talk about this first. Well, really because it leads to more complexity towards later. And okay, so in this case, the gauge transformation are Qij times e to the I phi I minus phi j, and Fi goes to Fi times e to the I phi I. So if you make these transformations, then even when Qij is non-zero, has a saddle point value, use, sorry, yeah. So this is the gauge transformation of the Qij. Okay.
Can you remind us what was the difference with the previous model you discussed?
So the previous model I had Qij as epsilon alpha beta, V dagger I alpha, V dagger j beta. So in that model, I would have a plus sign here, not a minus sign. Okay. Now the minus sign actually makes life very simple, because if I now take Qij and look at it, it has a saddle point value, which is Q bar ij on some set of bonds, then what I notice is that there's an unbroken U1 gauge symmetry. So then, if I make a global transformation, Q bar ij under phi that doesn't depend on sites, under global transformation, it'll just go to Q bar ij for phi I independent. So this means that, so I find some saddle point, and I notice that the saddle point doesn't change at all if I make a uniform transformation. So if I make a very slowly varying transformation, then the saddle point will change just a little bit, which will depend on the gradients of phi. And that immediately tells you that there is an unbroken U1 gauge symmetry. In other words, this U1 gauge symmetry on the lattice has not been hinged at all. It's totally unbroken. And you're going to get a photon coming out. Now, we saw the same thing on the square lattice here, but on the square lattice, we had to take a staggered gauge symmetry. We do a gauge transformation of just +1 on one sublattice and -1 on the other sublattice. And we got a photon there. And we said, that's dangerous, end of story, let's not look at that. And so there's a similar worry here. We're going to get a photon. It could have all kinds of dangerous effects. There's also monofolds and other things. So we need something else to rescue the day. So what rescued the day here was we went to a non-bipartite lattice. And what would rescue the day here is if we choose a Q bar ij to have a topological band structure, have a non-zero churn number. That's what's going to help make this saddle point a good point to start. But if I don't have a topological band structure, then you really have to worry about strong gauge fluctuations. But in this case, also you have to worry about, but once you have a topological band structure, the gauge fluctuations, although strong, can be understood, thanks to a lot of work that's been done on Chern-Simons gauge theories. Okay.
I'm confused about something.
Yes.
So let's trace the U1 gauge symmetry from the beginning. So
Yes.
this just from writing S in terms of F.
Yes, so now there's a U1 gauge symmetry here. Yeah, maybe I should, right, which is this one here. So that's always there, correct?
The original model didn't have any gauge symmetry.
Right.
You introduced it by hand by doing
Yeah.
that.
Okay.
And as a result, the characteristics of the gauge symmetry
Yeah.
are as if the model was Higgs. In other words, there could be a phase with a massless photon.
There is a phase, but as long, in this case, there is a phase. There always is a phase on any lattice for any Q bar ij. And that simply has to do with this minus sign here. With the plus sign, there was a
The minus
problem.
sign before could be changed by flipping B to B dagger on the odd sides.
Yeah, well, what if you don't have even an odd sides? So, right, so this is why on the triangular lattice, we couldn't rescue. We had, on the triangular lattice, no matter what we did, we found a Higgs boson. But with this thing, it's like life is different. You don't have to flip anything. You can put a triangular lattice, any lattice you want, there's always a photon. If this is your only Higgs field that you're worried about.
But there's no guarantee that there will be a phase. There are also phases without the photon.
If you do this decoupling and this is your only Higgs field, then there always is a photon. So you could imagine that you add another term here. You can take the original interaction and you can also add a term like Pij squared minus Pij epsilon alpha beta dagger alpha f dagger j beta. This is also something you can do. That's by, and you integrate over P and Q, you'll get the original Hamiltonian with some appropriate couplings. And now you look for a Higgs field, a phase where both P and Q are non-zero. Then you can get rid of the photon. But if P is 0 and Qij is as defined here, then no matter what lattice, there is always a photon. Yeah.
It seems that to solve, maybe it's premature, but it seems that to solve your problem with the U1 gauge field, it's F that should have band structure.
Correct. Yes, that's what we're going to do. Thank you. Did I say, if I said something else, I misspoke.
I thought you had Q, but maybe I
No, I meant F. Q will be the hopping matrix elements, which will give F the non-trivial band structure. Right.
So basically, the non-trivial band structure creates a Chern-Simons term for the gauge field.
Yes.
And that's why you don't have to worry.
Yes. So right. So I guess it's normal time. So so Tom said the correct thing. What will happen is, so now we have some Hamiltonian. Let's forget about this. And okay, this statement so far, and here's the argument again. So we choose some saddle point of this theory. The Qij is equal to some Q bar ij, some set of numbers. In this case, it will require them to be complex. Some of them will have some phases. But anyway, this is a fixed set of numbers. Now, what's the argument that this saddle point has a U1 gauge field? Well, the point is the following. If I do a uniform gauge transformation, then the Q bar doesn't change because of this minus sign. Okay. Doesn't matter what lattice I am. So let me make a slow gauge transformation. Under a slow gauge transformation, this means that Q bar will change with the gradients of phi. So this means that there's some component of Q bar, the fluctuations of a Q bar, which transform under gauge transformation by a correction depending on the gradients of phi. Okay, well, I'll write down what that is next time. And therefore, that correction to Q bar will be a gauge field because it transformed under gradients of phi. It'll be a gauge field with a Maxwell action at the minimum. Okay, so we'll come to that later. But now let's look at the effective Hamiltonian. So I have some Hamiltonian for the fermions. It's extremely simple. It's just some free fermion Hamiltonian minus Jij, Qij, dagger I alpha, dagger J alpha. Oops, sorry, no dagger, crucial. And then there's some chemical potential or constraint terms of lambda bar, F dagger I alpha, F alpha, which I have to choose to make the number density 1. Okay, so that's the Hamiltonian that I have to now diagonalize. This is Q bar plus summation conjugate. So this is some band structure on the lattice. So I get a band structure. So let me just give you the punchline. So the band structure will be characterized by what's called a Chern number. So every band in any Brillouin zone in 2 dimensions, you can associate with it a Chern number. It's an integer, which is usually 0. Okay, but for certain bands, it's some other integer, which is the Chern number. All right, so then you get a Chern number, which I'm going to call C. Okay, so then when we look at the gauge fluctuations, so the fluctuations are, we go about the saddle point. You get a gauge field A mu. And so you're going to get some effective action for the gauge field when you do the fluctuations about the saddle point. And you can get various terms, but a term that you're guaranteed to get, and this is what I will show next time, will be IC over 4 pi times this mu epsilon mu lambda mu A lambda. Okay, and this is d2x d tau. So that's the, in fact, that is the calculation in some level which Paulus first did, for which he got the Nobel Prize, was he first of all realized that this band structure has a topological invariant, which is now called the Chern number. He didn't call it the Chern number in his paper. And then he showed further that that Chern number was related to the Hall conductivity of that model. In this language, for spin-ons, that's just the coefficient of the Chern-Simons term in the emergent gauge field. So the paper by TKKN is precisely this calculation. Yeah.
So at the end of the day, the photon is not massless.
Right, right. Yeah, because of this. Right, so that's where we're going.
But before, I thought you argued that the photon must be massless.
I should have said there's a Maxwell term. That's the correct. There's a Maxwell term. under suitable conditions, there's an even more important term, which is the Chern-Simons term. So this argument here is simply the argument that it is definitely a Maxwell term with no Higgs field. Right.
So,
Yeah.
the thing, the band structure really depends on J times Q,
Yeah, sure.
right?
Well, let's take J to be some constant.
Oh, so just take J to be a constant.
Yeah, I'll write down some band structures. Yeah, the physical, it's just a dependent, you could have put a J here, over there. Okay, you can just redefine your Q if that makes you feel better. I did do it that way because sometimes the J's can have different signs, and then it's but if they're all positive, then that works.
The initial model was parity symmetric, right?
Yes, so this saddle point, once we choose the Q bar,
I see. So
you're broken time reversal symmetry. So this kind of mechanism has to spontaneously break time reversal. And that's also what's seen in numerics in certain models. You break time reversal. Okay. Right, so the task before us, and I'm running out of time, is first of all, you find the saddle point Q bar. Then, and the saddle point is such that the band structure of the F has a Chern number. Then you look at fluctuations, and the fluctuations are actually very simple. You get Qij is going to be Q bar ij, that's e to the I aij. And the aij, you can write as a line integral from Ri to Rj of some continuum field, slowly varying dr. Okay, so you have a saddle point, you perturb it slightly, and then you extend to second order in this. And you do it's a somewhat messy calculation, but amazingly the answer is very simple. And that's the calculation that TKK and paper. You find that you get this Chern-Simons term, as it's called, with the coefficient, which is exactly the Chern number of the spinons. What Thouless did was, for him, these were not spinons, they were electrons. He was talking about the integer quantum Hall effect. And this gauge field was the physical electromagnetic gauge field. And therefore, this was not a Chern-Simons term, this was the Hall conductivity. Okay, so it's just a question of perspective. I'm doing the same calculation that Thouless did in the spirit of my table, but for spinons, not electrons. And what that calculation gives, we'll say that a C is 2, will give you the Carlsberg. Okay. All right, yeah.
C is 2 just because F has 2 components.
Yes, that's why it'll be 2, right. There'll be a band with Chern number 1, and there's 2 components of that band. And so that gives you a certain set of statistics. So there's a whole, I could several classes which I'm not going to lecture, I'm just going to assert that once you have this Chern-Simons term, you can open up one of Edward's papers and figure out what the Semyon statistics, what the correct statistics of the actual spinons is because of the presence of this Chern-Simons term. That I'm going to move on to other topics, but certainly, I gave you this whole library of topological phases, and we could easily spend the rest of the semester just talking about a small fraction of that. But all of them, hopefully, feel at least some confidence in trying to understand them because they're all following essentially the same recipe here that we are seeing here. You've seen the 2 tricks. One is you have Higgs gauge fields, and the other is you have some topological band structure. With a combination of those tricks, you can understand almost everything. Okay. All right, well, I do have a minute or two, so let me at least draw the band structure that we're going to need. So the band structure we want is the following one. So take a square lattice, but you need diagonal bonds. We're also going to have bonds on the diagonals. Okay, And you're going to choose a band structure so that the flux, the product of the phases of the bonds around every plaquette is I. So that's what you want to choose. And that will give you a band structure with a non-zero Chern number. So there's a picture. So T1, so this T1 refers to Jij, Qij. Okay, so T1 is T1 here, T1 minus T1, minus T1, T1. Yeah, there may be a typo in this picture. Okay, better not try it. Then you have to give these guys arrows because they're complex numbers. Okay, anyway, so these are I, T2 with some arrows. So you have to choose the T1 and these factors of I and the orientation of the arrows in a way that if you go around anti-clockwise and any triangle, you get I. So it's a uniform flux. So for some reason, it could just happen. The energy is minimized by these things having a flux of pi over 2 in every triangle. If that happens, you get a band structure that has a non-trivial Chern number. So that's what we'll talk about next time.
If you had -1 instead of I, that would always give you direct fermions.
You mean the diagonal bonds are 0? Then you have flux pi per plaquette, then you get direct fermion.
Yeah, oh, I see, okay.
So if the diagonal bonds are 0, so the T2 is like the mass of the direct fermions. For small T2, you can write it in terms of continuum theory of massive direct fermion. There's 4 of them. And so then you can, you don't even need to know about Chern numbers. You can just compute the one loop diagram for massive direct fermion and figure out what the Chern number is. You don't need to know the lattice definition.
Yeah, but that's what I was saying. So you're saying that's the way to get.
So that's the quickest way to get it. So there's 2 ways of getting the Chern number. The correct way is to do the full calculation on the lattice with no approximation. The other is to take the low energy limit when T2 is very small. So that gives you the continuum theory of massive direct fermions. And that also gives you 2. But that calculation doesn't tell you why there's no correction from all the terms you left out. But there are. I mean, in some sense, it has to work. In some, yeah.
I think it probably is an argument.
Yeah, you have to, right, maybe you have to introduce the eta invariant or something like that. Anyway, I only understand the way of doing it on the lattice. Yeah, it's not obvious that there will be no corrections from the high energy part, because when you compute the Chern number on the lattice, it comes from all momentum. It's only an integer after you integrate over all momentum. But when you take the direct fermions and integrate over not a Brillouin zone, but from 0 to infinity, you get the same answer. I think it has to work out, but yeah.
I think this is the way anomalies always work.
I see. Okay.
That calculation is insensitive to UV stuff.
Yeah, you're right. Okay, yeah. I mean, I think the fact that it's an integer kind of tells you it can't change to any small deformations. Yeah. All right. Okay. So sorry for the technical difficulties, and we'll actually compute a Chern number next time. And there's no lectures next week, so we'll be back on November 1st, I believe.
As you said, TKNN interpreted their calculation in terms of the.
Yes.
But who or when interpreted it in terms of a Chern-Simons coupling of the electromagnetic field?
Chern-Simons couple. Well, I don't know. Before that case, why is it a Chern-Simons term for the electromagnetic
Yes,
field?
that interpretation of the Hall conductivity and the integer quantum.
Who did that? Well, that's probably. I don't know. I mean, I think there was Zhang, Hansen, Kibelson. There was, yeah, probably, or maybe it was, yeah, I think it's probably them, or maybe it was Irvin and McDonald, and there was, of course, also Nick Reed, and then there was Wen. So there were many people talking about it. I'm not sure. I'm sure it's a sensitive point, but I would suspect it was probably Gervin and McDonald probably had. Yeah, Gervin had some lecture notes I heard about. I heard about it from him first. Yes, I'm pretty sure.
Thanks.
Yeah.
So the Partonic interpretation of the Jane theory,
Yes.
that exists in the literature, is that
Well, Jane talks about it in his very early papers.
really?
Yes, and then, but the gauge theory using Jane's construction, I guess there was papers that Bloch and Wen that were written on Wen was the postdoc here.
Perfect.
But again, they're very hard to read today. It can all be cleaned up, and that's in my notes. Well, okay, cleaned it up for my own style, I suppose. But in principle, I'm sure Wen understands it. For the UPM, I did.
Yes.
Okay.
All
All right. Yeah,
So
so
we'll see how many people come, because there might be some complicated logistics.
I've not been getting any UPM emails at all. Recently you sent, maybe Mike sent it?
Mike, I decided I'm not sending any emails. It's
Okay.
all Mike, because otherwise there would be
Okay, I'll take a look.
too many cooks.
Well, also, okay, thank you. I'll try to come, although my
I-
daughter's going to be here that week.
Right, so everybody has their own constraints. But please let me know early, because at some point, since there's a logistic constraint, at some point I will just stop the registration if there are too many people.
Okay,
There is a cutoff of 12. I'm not sure how hard cutoff it is, but
okay,
I think 12 is more or less what the number is.
okay, we better, hopefully this is not being broadcast.
Well, doesn't matter, they cannot show up.
Subir,
Yeah.
I just wanted to say this was a spectacular one.
Yeah,
Thank
this
you.
is,
So,
yeah, it's absolutely fantastic. I sit there crazy taking notes.
because I'm very
It's
proud of those
only your
tables. I spent the last 2 days thinking about those tables.
Yeah, no, the tables put a lot of things that I did not know how they're connected.
No, it was
beautiful.
just beautiful.
Beautiful. And the fact that you get questions from the audience means that it is interesting. The alternative is that everybody goes to sleep.
Yeah,
So, right, this is much worse than getting questions.
yeah. Okay, thank you, thank you. Yeah, that was fun. I'm learning. I mean, it's really been very valuable for me to just to give a lecture that you guys will appreciate.